In this video, we're going to take a deeper look at the fundamental theorem of calculus. Now, the fundamental theorem of calculus is fairly easy to take for granted because it's fairly straightforward in that the part one states that the area function or the integral and the slope or the derivative are opposite operations. So if we take the derivative of an area function, we get the original function back. So they essentially undo each other. So here, part one says that if with the integral or the area under f is a, if we take the derivative of a, we get the original function f back. The second part of the fundamental theorem of calculus states that the area under the curve is calculated by the displacement on the antiderivative. So those are two main ideas of the fundamental theorem of calculus. Now, we want to take a little bit deeper look at this and do this a little bit more rigorously. So to do this, we first of all want to establish that the area function is the function under a curve from some arbitrary starting point A to X. And as we move that X along, so if I sketch this in here, if I draw in a line here, that point represents X, and I take that point, and as I move it left and right, we have a different amount of area to the left of that line. Okay, and the amount of area that we have is going to be our a of x function. So we're establishing our a of x function, and we also know that that area is the sum of all these Riemann sum rectangles, and if we take the limit, we end up with this area function. So the area function is defined as the area underneath this curve as we move some point x along the horizontal. How can we formally connect the area function a of x to the antiderivative big F of x? So we have this a of x function. This is the red area, and it changes as we move along the horizontal. So depending on where I stop the x, we're going to have different amounts of area. What we're going to look at then is how does this area function change? So we need to find the change in this area. And we find this change in this area with this small rectangle, the blue rectangle that we've drawn here. So if we think about this area function is the a of x is going to be this area here, all the way up to x, and then the a of x plus h is going to be all the area, including this blue area, all the way back to a. To find the difference then, we're just going to subtract those two areas. So I have the area of the rectangle is going to be calculated by a of x plus h minus a of x. And that's going to give us that blue area, approximately that blue area. And that blue area can be found by taking the height of that rectangle, which is our f of x, and then multiplying it by the width of that rectangle, which is h. So that rectangular area is going to approximate the change in the area function from x plus h to a of x. Now, although this is an approximation, as we let h get smaller and smaller and smaller, we know that that area of the rectangle is getting closer and closer to the difference in the a of x function, or the change in the a of x. And if I rearrange this expression and let the limit as h go to 0, which I'm doing here, I can see that I'm going to end up with the exact value of my f of x function, which is what I had here. Well, what that means then is, if you look at this expression, that is the definition of the derivative of a of x, which means that f of x is the derivative of the area function. Well, if that's the derivative, f of x is the derivative, then a of x is the antiderivative, which means then that we can formally connect this idea that a of x and f of x, big F, are the same thing. So we can also then use the converse of that. So conversely, the sum of the rectangles is the difference in the antiderivative. So we can say that big F at B and minus big F at A is going to give us the area under that antiderivative, or the area under the f of x function, or my definite integral.